Hi, my name is Brandon, and this is my solo final validation. Alright, go ahead and jump right in with our first one, number 2. Awesome, so number 2 right here, bring up, if you see it. It asks to find the limit as x approaches 2 from the left as well as 2 from the right of the graph of f of x. And looking here, I see a f of x at from the left approaching 2. So from the left coming down here that approaches 2, it looks like it is going to be a negative infinity here. Sorry, and then from the right side, it actually comes up and hits. It looks like it hits 4 there, and that would be. Oh, it actually just says right here it's 3. I was wrong. Um, but that's just looking at just the problem here, but looking like what's actually behind the problem, actually looking at the limit and what exactly the limit is. It's fairly simple, but right here you would state it's the limit as x approaches 2 from the left, indicated by the little minus sign at the top right of the number of f of x. That's how you would say the problem, and then really looking at it when you're trying to solve for limits, you're gonna have to have a graph. You can solve it with numbers, but this time we're given a graph, and you're just looking. There really isn't much calculations involved. You're simply just looking whenever you're given a graph. So it says as x approaches 2 from the left here, you just follow the left side all the way and just see what's really happening at 2, or really any given number, and that's just your answer right there. It's fairly simple, and that's pretty much it for number 2 and the calculus behind it. Go ahead and go to the next one here, which is number 10. Well, that skipped far. 10 is not in this here. Our group mate forgot to put it in here, but 10 was one of the ones I did. It's a graph. Let's see, where is it? Yeah, it's a little. I don't know if you can really see that, but I got a little graph. All it really says to do here is just to graph the functions f of t and g of x, and then just to circle um, the the parts of the graph that behavior is actually the limit at infinity. And all I had to do there was just circle the endpoints on like the not the endpoints, but the kind of right ends of the graphs, because as it's saying, as x approaches infinity, as just x just getting larger and larger. So you're looking at the right side of the graph and circle what the graph is doing at that point, and g of x is actually just steadily increasing, so it's going to go to infinity, whereas f of t is just kind of flatlining, getting very close to 0, not quite at 0. I believe it might be at 0. So that one would just be 0, and it's again with these limits that it's just really you're just looking at it and just seeing what it actually means of that limit, and of whatever x is approaching. As x is approaching infinity, you're just gonna keep looking, what is the graph doing, what is the y value as x is getting larger and larger, and that's gonna be your answer. Let's see here, next one is 13. All right, so 13 right here. Go ahead, pull this up. That is a very blurry picture. So hopefully you can actually read that, but I'll read it. The item 13 states that the simpler integral in item 12 is called a basic form integral. Your goal is using any integration technique is to transform the original integral into a basic form integral that are listed in an integration tables here. So looking at this one, it's not actually asking me to solve the integral, it's more asking me just to turn it into a basic form. A basic form can easily just be translated to a more easily understood form of what you're looking at. And it's fairly simple because it's working with substitution. You probably can't read that up there, but I state that u is equal to x squared, so you're going to replace the x squared with a u. So instead of looking at it as x times the sine of x squared, you can look at it as x times the sine of u, which is fairly easier to comprehend and look at. The substitution very simplifies it down, and that's what it's asking for. It's asking for it to become a basic form integral, and that's just simplifying it down, making it easier to look at, maybe a little bit easier to understand, and it's very achievable with substitution. And the calculus behind substitution really is just to get it to easier. It's to make complex things a lot easier, and it does that. This is a fairly simple integration, so maybe it's not too much more simplified. However, in more complex problem substitution can be very helpful. It just really negates those extra steps, those tedious work you really have to put in there with not using substitution as we did before we learned the integration by substitution method. But that's basically really all the substitution method does for you is just simplifies it down, makes it a lot easier to understand, even to look at and to grasp when you're trying to do these. And then let's see here. Next one is 20. All right. So 20 right here. Flip to that. So 20 states after all the work for integration by part IBP, we finally get the answer for the original integral right here. And then it asks here, so it says if we check our answers by taking a blank of our resulting answer, we should have to use the blank rule to differentiate. That is the integration technique blank by blank and versus the blank rule. This one really plays on, well, first of all, just the integration, and it looks like it's fairly simple, asking for another substitution here to simplify a more complex interval down, and then is asking for the final integration as well as kind of how to check your work and playing on the fact that the derivative is the inverse of integration. Very important stuff, very important rules here. Um, the calculus behind this, obviously, integration and the substitution rule. Substitution being very important to simplify those complex problems down, and the integration, the integral or the antiderivative here, um, is also another part in the calculus. Very helpful. It, in my experiences using this in this class, using the antiderivative or the integral, it's for me, I believe it's more to find pieces of the missing puzzle to solve your problem, like given given the acceleration function of a graph and what the velocity of a certain time frame is, then you can figure out the velocity function and the position function, and that's just given so little, you can figure out so much with integration. It's very neat. And again, it plays on here, it says to use the product rule to differentiate because the integration by substitution inverses the product rule. It also inverses a couple other things. You also have to just like look at it. I believe that should have been by parts, but I'm not quite 100%. I did not do this problem. But it's really playing on the fact that derivatives and integration are the inverse of each other, which is very handy because you can check your answer because you're always given, like up here, you're given a problem, a function to differentiate or integrate, and then after you take that integration, you can just take the derivative of your integration to figure out whether or not you did it right. Very helpful. The next one here is 15. I don't know why that wasn't in order, but 15, where is that? Ah, here we go. That is back on the terrible picture. So 15 states, if you compare the two integrals you have analyzed and evaluated in items 11 through 14 and items 16 through 20. All right, now I see why it's in this order. So the integrals are very similar. When integrating functions, you must be able to determine which technique is appropriate. Explain how you would know when to use the integration by substitution versus integration by parts. This is my answer here. I'll read that because on top of bad handwriting, looks like it wasn't all that great of a picture. Um, so I state that you use substitution when you would need to use the chain rule if you would have had to take the derivative. And then in parentheses here, I say on composite functions. When you see a function that looks like it's going to involve more steps, perfect example is just right here. When it says x times the sine of x squared, you're going to say, well, there it is. There's the parentheses and more stuff is happening to the x inside of those parentheses. You're going to need to use the chain rule, which means that it's a composite function, which now you know that substitution is what you're going to be using here to make it a lot easier than just straight up taking the integral. And then I state after this, you would use the IBP, which is the integration by parts, for less complex functions like simple products, sums, and differences. Sums and differences is kind of on the more very easy side, but like products, you would see that in the items, say 16 through 20 that we just looked over, you use the integration by parts because you're using products instead of anything special really happening. It's not a composite function. There isn't a lot of extra things. It's just the products happening. So you can use the simpler version of integration, which is just the integration by parts. And I hope that makes sense. And it made sense to me when I wrote it, and even now. The calculus behind this, I think, is just even more playing on how the inverse nature of derivatives and integrals really play into understanding the integration and integrals, all that stuff. I think it helps you understand it. It helps me understand it. Like even here, I say that you would know that you would have to use the substitution when if you would have had to take the derivative, you would have used the chain rule. Um, that's just it helps me understand, and that's pretty much it for this problem. Let's see here. The next one I believe is the yeah part 3 here. That is on the apply side of things. So, all right. So item 3 right here states a population of honeybees increased at a rate of R of t, which is just the rate function, bees per week, where the graph of R of t, which is the rate function here, is shown, and it's not shown here, but it's on the other page. Determine m with a subscript 6 to estimate the increase in the bee population during the first 24 weeks. Write an explanation of your process. Um, I did not do this problem. Our classmate Eli did. But looking at it here, you would use the calculus behind this is going to be the area under a curve, area under a graph, whatever. which is gonna be using rectangles. Uh, and it looks like you got a graph here, and obviously it's probably hard to graph rectangles, but um, you'd use the rectangles method to get an estimate, because that's all it's asking for. Determine using it even says in subscript 6, which tells you to use 6 rectangles to estimate the increase in the population. Um, there's a couple ways you can go about doing this. You can use left endpoints, right endpoints, midpoints. Um, I think personally, it actually says M6. You actually might need to take midpoints here. Um, which is a better guess because left endpoints and right endpoints, they can be over. They can be over, under, and midpoints are generally pretty close to that answer. The how to get the actual answer here would be the integration, the definite integral actually, because it's over an interval. And the calculus behind this, it's kind of weird. You used rectangles. It seems more like geometry than calculus, but it's the area actually underneath a curve, and it's just so simple. It's weirdly simple for calculus because you're just drawing rectangles. It's gonna go up and over all the way just to get an estimate, and it's very neat. And then see here, B. There isn't a B. Oh, I found the B. Create a numerical table representation of the rate of RFTBs per week as a function of weeks using the given graph. Then use Desmos to find the best curve. Once you determine the rate function, use the function to determine the increase in bee population during the first 24 weeks. That is on the first interval 0 to 24 using the fundamental theorem of calculus. Provide a screenshot of your Desmos work. Okay, so this is the curve here, and you can see the tables that Eli made to do this. And it wants, so see, is asking for to find the best curve here, the best curve function for the rate, and then to use the fundamental theorem of calculus, and that's the calculus behind this, is the fundamental theorem of calculus. Wouldn't really know it by hearing the name. Um, fairly fairly simple. The fundamental theorem of calculus, one of the last things we did here. Um, you can see Eli had his tables, and then see here his work right here. See, he started by plotting all of the points to find the, I guess, curve of best fit might be a good word to use here. And then, see here, yeah, then makes a table to calculate the, can't quite read that there. The y values, x values, and all this to figure out what he did here. And then, kind of hard to follow. Yeah. All right. So yeah, and it says, yeah, I added up all the y values and stuff to get his final answer here, which I believe, yeah, this is the fundamental theorem of calculus. Um, this is a awesome applied problem to have, as it really works with some cool stuff. The area under a curve, which is great. How it really points out the application of integration there. Very, like, just really well points that out. Um, I mean, that is for the definite integral, and then also the fundamental theorem of calculus comes into play, and you can really see the application of that in this problem too. I mean, it even tells you just to use that. Very, very good stuff, and that's it for these. So now it's on to my favorite, apply for the whole thing. And honestly, I don't. Yeah, right here. Before this, this is actually my favorite one now. Well, if I had to choose, but it used to be I really liked doing the exponential growth functions and decay. I always thought those were very cool as I saw more practicality in them. However, I really like before the exponential growth when we didn't actually work with that yet. I liked the position questions. It gives you a position function and then tells you to find the velocity of it, the acceleration of it, explain what it means and all of that. And you really do that in the number two apply problem here. It gives you the position function and then it asks you to write out in complete sentences and explain your thinking of it. And I really like that type of stuff when it goes on here to just be given position and to figure out its velocity and its acceleration and what it means and how you know it. Really like that, and that's just why that this is my favorite one now. It's good, good place to end off our semester. Um, see what part of your own practice has impacted your learning of the attitude about calculus? Um, well, a lot of the time my own practice, I'm gonna take that as in like what I did on my own to try to figure out these things. And really what I did was YouTube videos of other people more accurately. I watched videos on the organic chemistry tutor, which he also teaches calculus apparently. Um, and those videos really helped, and it makes it just seem very simple. And then what the stuff that he didn't really go over, obviously, I got from the videos that were posted in our Canvas there on this class specifically to get the stuff, especially the vocabulary. The vocabulary was big on because I didn't really know like what things meant what. Obviously, other YouTube videos didn't teach you that. I had to go to the videos for that, which should anyway. But it affects my attitude about calculus. I always knew that calculus was going to be difficult, and I think it was not even a semester, as like not even half of a semester back in high school of it, but I ended up dropping the class because it was during COVID and our school was not equipped to teach people how to do stuff online, especially not my teacher. So not gonna do well in that one, so I dropped that. But I was able to carry over some things about that, so I was kind of had a good attitude about going into this because I knew I already had seen it. It wouldn't be that brand new to me. And then by the time that this stuff I caught up to where I was, um, that stuff wouldn't actually be all that more difficult considering I got everything before it from my last class. Getting to the new stuff was not going to be as hard because I've already kind of seen what calculus has to offer. So my attitude going in was mostly positive, and getting through it, I mean, I'm not going to say it was a breeze, but it was definitely not as hard as I expected it to be. But from what I've heard of Calculus 2 and knowing nothing about Calculus 2, besides the fact that the fundamental theorem of calculus is in it, it's gonna be hard. And that's kind of my attitude about it. Um, for what parts of your instructors has impacted your learning of the attitude about calculus the most? Um, the Zoom meetings, I guess not Zoom, the Cisco WebEx meetings that we do every Thursday and Tuesday. So usually when I did online classes, going to those like always just like for me it sucked. It was kind of like a waste of time, but in this class it was great. Actually, yeah, it was really great. Because if I ever needed help, I could always ask questions, and I surprisingly didn't. I don't think I ever even asked a single question. I've always kind of understood because the way that my instructor taught this was it was slow enough for me to like not get left in the dust. I could actually keep kind of going with it. Um, sometimes taking notes. Most of the time I didn't, but sometimes I wrote a few things down just because I thought I might forget it. I ended up not forgetting it. I don't think I've even looked at my notes, but that's kind of how it is. And it impacted my learning of of and attitude. Learning helped a lot um, with the Cisco WebEx meetings there. Like I said, I've already seen a lot of what Calculus 1 had to offer, and then going into it, and then like it just a re-explanation of it really helped. It was nice, and the attitude about calculus, it made me feel better about it because I thought it was gonna be kind of like I've already seen it, but it still might be hard when I get later into it. And then after the first like couple weeks, I realized that this class is not gonna be as bad as I originally thought, even even if that was a already positive view. And it looks like that's it for this video. Um, thank you.